Good morning, everybody. What a wild morning. This has been crazy, but I'm glad we have Zoom so that we can do this. Will you guys let me know if you can hear me? Either somebody say something, someone give me a thumbs up, somebody put something in the chat. Okay, people can hear me. Okay, awesome. I am curious how much snow accumulation you guys got. How much snow did you get? Either say it or put it in the chat.
I think I got like 3 to 4 inches at my house.
Okay, 3 to 4, not too much. At least 3
I think-
inches, maybe more.
I think I got like 8 inches.
8 inches? Wow.
I'll show the camera real quick.
Yeah, I was like, I think Emma's gonna show us how much snow she has.
Y'all gone outside? Wait, is my mic working?
Yeah, it's working, Dante.
Yeah, I can
All
hear
right.
it.
Check that out. Look at Emma.
What the dog doing?
I think at my house we have like a whole foot. I'll show you guys.
I guess I can
Yeah.
unmute myself.
Yeah, our backyard's
Wow.
like covered.
That is crazy. Yeah,
Everything is covered.
let me show you what my house looks like. That is insane. You have more snow than we do. Ooh,
Yeah, it's a lot.
this is my house.
Oh,
You see
wow.
that? Yeah. That's how you get out of
Jeez.
my house. And it's still snowing. It is still coming down. It has not stopped for like 12 hours. Anyway, wildness. Glad we could meet over Zoom. And good for you guys for coming. Wait, I'm sorry. Who did I see all the chat things? I love it. Okay. Well, as I said in the announcements, I'm just going to finish the notes that we were planning to finish in class. And then we'll do a little bit of the homework. I think I'm going to reduce the homework assignment since we're not together and since we only have an hour to work on it. So I guess thank you, Snow, for making that possible.
Are we also pushing back the test date, or is that remaining the same?
That is probably going to remain, well, it will probably be Thursday, Friday instead of Wednesday, Thursday now.
Are we still doing the late start hours?
Yes and no. If your teachers wanted to follow that, they could, but a lot of the teachers are just going to have you watch a video or do assignment or something and just be
So it's not really like a set schedule.
No, you don't have to go to class at a specific time. I just thought Zoom would be easier so that I could at least answer questions. Okay. Does everybody have the notes available? Good. Okay, thanks. Okay, I'm going to share my screen. Okay. Are you guys seeing the screen of notes? I can't hear it. I'm not sure why that's a thing. Okay.
Have you tried joining with computer audio? That was what caused me to be able to hear it. You can try leaving and rejoining and changing your audio source.
Whoever it is, I hope they figure it out. Oh, I got unplugged. Okay. I'm probably gonna turn my camera off because you're gonna be looking at my ceiling. But if you have any question at any point, just let me know. Okay, so I believe that we're on part B. Someone correct me if I'm wrong, but I think we did part A on Friday. So we're gonna pick up at part B. So events A and B are independent if and only if they satisfy the probability A given B equals the probability of A, or the probability of B given A equals the probability of B. So let me tell you what that says. In the last lesson 8.2, we learned one way to check for independence. That was the probability of A times the probability of B equals the probability of A intersect B. So if you remember, we found those two sides of the equation, and if they equaled each other, then the events were independent. And now that we understand conditional probabilities, there's a second way to check for independence, and that is what this paragraph says, which says the probability of A given B will equal the probability of A, or the probability of B given A will equal the probability of B. Any of those will work. Somebody's having a hard time connecting to the audio. Would somebody be willing to chat with them to try to help them get connected? Dante, you sound like you know what you're talking about, so maybe you could send them a message in the chat.
Yeah, I only use Google Meet though, so I'm just yeah. I'll try. I'll try.
Okay, thanks, Dante. Okay, so let's look at how to check independence this way. So example 3 says a bakery sells vanilla and chocolate cupcakes with white or blue icing. Are color of icing and cupcake flavor independent? Okay, so we are gonna check these two things. We're gonna check the probability of blue given vanilla, and we want to know, is that equal to the probability of blue? Okay, so let's find the probability of blue given vanilla. And it's been a minute since we did this, but to remind you, how we find a conditional probability is you do the probability of the intersection of the two events divided by the probability of the given event. So for this one, the probability of blue and vanilla is 5 out of 21. And the probability of vanilla is 8 out of 21. If we flip over our fractions, cross out the 21, we find that the probability of blue given vanilla is 5 out of 8. Okay, so that is this first one right here. I'll do the other one in a different color. So this one, let's find the probability of blue. And the probability of blue will be 12 out of 21, which can be reduced, so they're both divisible by 3, so we'll get 4 out of 7. Okay, and now the question is, are these two things the same? No, they're different, right? And because they're different, we can conclude that these two events are dependent. Dependent. So again, you check that conditional probability, find out what it's equal to, check your other probability, find out what it's equal to. And if they are the same, it'll be independent, and if they're not, they'll be dependent. Are there any questions about that example? Okay, awesome. What the bottom of the page says is that we can actually use any of the colors of ice creams and the cupcake flavors to check independence. We did blue given vanilla, but we could have done blue given chocolate, or chocolate given blue, or chocolate given white. As long as we set it equal to the appropriate probability, we could have checked independence using any combination of cupcake flavor and icing color. So these would produce the same result. Okay, let's go ahead. If you have your homework, pull that out. And let's go ahead and do one of them from your homework together. And we'll do, I'm on page number 3. And I'm going to do number 1. So is the probability of having good grades as a goal independent of gender? Okay, so we're looking at good grades and gender. Okay, so let's do the probability of grades, right? That's what this one is. This is the grades thing. Probability of grades given, you can either do boy or girl. Let's do boy. So the probability of grades given that they're a boy has to be equal to, and then it's always equal to the one that's not known, which for this one is the G. So that will be equal to the probability of having good grades as a goal. Are those independent? So the probability of good grades given that they're a boy, well, if we just look at the table, we have a total of 227 boys. 227 boys, and of those 227, how many want or have good grades as a goal? That's 117. So that would be that conditional probability. And then the other side, the probability of having good grades, how many people have good grades as a goal? That's 247 out of our total number of people, which is 478. So, you guys have a calculator either on your phone or on your computer or something. Will you guys find both of these fractions in decimal form? And once you have it, put it in the chat. I just don't have a calculator nearby. Sorry, this is not letting me scroll through the chat. That's annoying. Anybody get those in decimal form? Carson, what's up? Is this what you need, Carson? This right here? $19.2. Let me find a calculator. Okay. Carson, I'm gonna scroll down, so if you need it, take a picture or something. Okay. So back to the homework assignment. We've got 117 divided by 227. I get 0.515, and then 2447 divided by 478. I get 0.517. And are those the same? No, they're different. And because they're different, we'll use these 3 dots to say therefore they are dependent. Okay. So again, that's how you check independence, using a conditional probability. Check the 2 things. If they're the same, independent. If they're not, they're dependent. Okay, I'm sorry if this gives anybody motion sickness, but I'm going to go back to page 4 of our notes. And we're going to look at checking independence using a Venn diagram. So the question is, are having an iPod and having a cell phone independent? Well, let's do it. So we would do the probability of an iPod, let's say, and having a cell phone. So given a cell phone, we want to know, is that equal to the probability of having a cell phone? Okay, well, the probability of iPhone given cell phone will be the probability of iPhone intersect cell phone divided by the probability of cell phone. And let's find that. The probability of iPhone and cell phone is 10 out of the total number of people, which is 35. Over over 25 out of 35. Which if we do the fraction thing, that will come out as 10 over 25, which is 2 over 5. So that's this side, and then we'll do blue to find this one. The probability of having a cell phone is going to be 25 out of 35. Divide each of those by 5, we get 5 out of 7. Did I do that right? No, I did that backwards. I apologize. This is supposed to be iPod. That makes more sense. And the number of people who have an iPod is 14 out of 35. And if we simplify that, we get 2 out of 5. And since these are the same, they are independent. All right, does anybody need me to repeat any of that? Okay. I hope this is making sense. I have no idea how to know if this is making any sense. Chat, how do we know which is the given? The given, so if you're checking independence, it doesn't matter which one is the given. You could have done cell phone given iPod or iPod given cell phone, as long as you choose the correct probability to set it equal to, which is going to be the thing that's first. So set it equal to the probability of the thing that's first. Any other questions? Okay, part C. Here is the vocab. So a compound event consists of 2 or more simple events. Tossing a coin is an example of a simple event. Tossing 2 or more coins is a compound event. A compound event is shown as, this is how we would find the probability of this. find the probability of A intersect B. It's the probability of A times the probability of B. We've seen this equation before. This is the equation that we use to check if things were independent. So that's how we find the probability of a compound event when things are independent. We'll talk about what to do when they're not independent in a minute. A tree diagram is a way of illustrating compound events. Each simple event adds new branches to the tree diagram. The end result shows all possible outcomes. Okay, so I'll show you how to draw a tree diagram here in a second. And then the last thing says when events are independent. So as I stated earlier, this is what we're talking about right now applies when things are independent. The probability of the compound event is the product of the probability of the desired outcome for each simple event. This is the general multiplication rule. So all of that was a really fancy way to say when we're talking about independent events, you just multiply the probability of each event together. Okay. Example 5. So it says this is a tree diagram representing the possible outcomes when tossing 3 different coins. So that's what we're doing here is tossing 3 different coins. So let's draw a tree diagram. How this works is you have a starting place. And then you show the possible outcomes of the first event. So if we're flipping 3 different coins, the first event is flipping a coin, and the possible outcomes of a coin are heads and tails. What's the probability of getting heads? 1/2. The probability of getting tails is 1/2. So along the branch, you show the probability of getting that option. So right here, this represents our first coin. Then from each branch, we show the possible outcomes of the next event, which is again flipping a coin. So if we got heads the first time, when we flip the second coin, we could get heads and tails again. And if we got tails the first time, we could get heads and tails again. And the probability of each of those is still 1/2. This would be the second coin toss. And then the third time we toss a coin, again, from each branch, we show the next option. So we can get heads and tails, heads and tails, heads and tails, heads and tails. And the probability along each of those branches is just what's the probability of getting the outcome, which is 1/2. And this would represent the third coin. Okay. And now we want to list all of the possible results. Maybe to help you understand how this works. So to see the possible results, you'll just follow the branches. So our first possible result is we could get heads, and then heads, and then heads. So our first option is heads, heads, heads. Another option is heads, heads, tails. We keep following this pattern, we could get heads, tails, heads. We could get heads, tails, tails. I hope you're seeing the pattern here. I'm going to keep going. So then we could go down and we would get tails, heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. So how many possible results are there from this combo event thing? That would be 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible results. Okay, so then we can use our tree diagram to help us to figure out the probabilities of getting certain results. And the way that we use the tree diagram is we just follow the trail that gives us these 3 options, multiplying every probability that we walk past. So the probability of getting heads the first time is 1/2. Then the probability of getting heads after that is 1/2. And the probability of getting heads after that is 1/2. So the probability of getting heads, heads, heads is all those things multiplied together, which is 1/8. And then we can do the same thing for finding the probability of tails, heads, heads. Probability of getting tails the first time is 1/2. And the probability of getting heads the second time after that is 1/2. And the probability of getting heads after that is 1/2. So the probability of getting tails, heads, heads is 1/8. That was a not very interesting example. Because they were all 1/2. Any questions about that example? Okay. I think we are going. Let me decide. Just a second. Okay, yeah, we'll do this next one. So this is a tree diagram representing the possible outcomes when tossing one coin and rolling one die. So those are the 2 things that we're doing. So let's go ahead and make a tree diagram. So we'll have our start. And then we think, okay, what are the possible outcomes of the first event? Well, we're tossing a coin again. So we're either going to get heads or we're going to get tails. What is the probability of getting either of those? Again, that will just be 1/2. Okay, and then to simplify this rolling the die, what we're going to do is we're going to say, okay, we're either concerned with getting a 1 on the die or getting a not 1 on our dice. So the probability of getting 1 on a 6-sided dice is 1 out of 6. And the probability of getting not 1 on a 6-sided dice would be 5 out of 6. And then the same possible outcomes will happen if we get tails the first time. So that will be 1 and not 1. What's the probability of getting a 1? That's going to be 1 out of 6. The probability of getting a not 1 is 5 out of 6. Okay, so let's just find a couple of things. Let's find the probability of getting heads and not 1. Well, again, all we do is follow those branches. So the probability of getting heads is 1/2. And then the probability of getting not 1 is 5 out of 6. So the probability of getting heads and not 1 is 5 out of 12. And then one other example, let's do the probability of getting tails and a 1. Go ahead and find that on your own. Okay, the probability of getting tails is 1/2. The probability of getting 1 is 1/6. And so the probability of getting tails and 1 is 1/12. Okay, so that is how to use a tree diagram. Let's go ahead and look at your homework. So we are now going to be on page number 4. And we're going to look at number 1. So it says, using a tree diagram, find the following probabilities. Sophomores are required to either take English 10 or English 10 honors. They need secondary math 2, secondary math honors, or pre-calculus. And then sophomores also need biology or chemistry. And part A says, draw a tree diagram representing all sophomore choices. Okay, well, we know we'll have a start. Okay, so go ahead and look at those things. And what are our possible outcomes of their first choice? Well, their first choice is the English choice, right? They can either take English 10 or English honors. So their first choice here, they can either do English 10 or English 10 honors. I will tell you right now, there's not enough space on this page to make this tree diagram. Okay, what's the probability of choosing English 10? Well, let's just say it's 1/2. And the probability of 10 honors is 1/2. Okay, now what are the possible outcomes of their second choice? Well, the second choice is about math. So they can either do secondary math 2, secondary math 2 honors, or pre-calculus. Secondary math 2, secondary math 2 honors, or pre-calculus. So this will be secondary math 2, secondary math 2 honors, and then pre-calculus. And then again on the second one, secondary math 2, secondary math 2 honors, or pre-calculus. If there's an even chance of them picking a specific class, what's the probability of choosing secondary math 2? Well, that will be 1/3. Secondary math 2 honors will be 1/3, and pre-calculus will be 1/3. And then the same will go for the bottom portion of our tree. All right, on your own, go ahead and finish that tree diagram. They have one more choice to make. Okay, so their last choice is the science class that they take. That's either going to be biology or chemistry. So on all of the ends, we're going to put biology and chemistry. And then the probability of getting each of those is 1/2. For lack of space, I'm not going to write it on every branch, but I think you understand the idea. Will you give me a thumbs up if you got that tree diagram? Okay. Awesome, awesome, awesome. Yay, okay, good. Thank you. Okay, I think we're understanding tree diagrams. Okay, let's go back to our notes. And we have one final page. So everything that we just talked about applies to independent events. What we're going to talk about on this page is the probability of dependent events. So the probability of two dependent events is as follows. If two events A and B are dependent, then the probability of both events occurring is the probability of A intersect B equals the probability of A times the probability of B given A. Okay, so in other words, the probability of both events occurring is the probability of event A times the probability of event B given that A already occurred. Likewise, the probability of B intersect A equals the probability of B times the probability of A given B. So what each of these says is this thing is given the second time, right? The probability of B happened, and then the next second time we know that B happened and we're trying to find A. And this is going to be a little more intuitive than I think it seems. So let's do example number 7. So it says there are 7 dimes and 9 pennies in a wallet. Suppose 2 coins are to be selected at random without replacing the first one. So that is why they're dependent, is because we aren't replacing the coins. Find the probability of picking a penny, then a dime. So the probability of picking a penny and a dime. Okay, so we can either use the equation or we can just think about this. How many total coins do we have? Well, we have 7 dimes and 9 pennies. So there is a total of 16 coins. What's the probability of getting a penny? Well, it's 9. Okay, so that's the probability of getting the penny the first time. Then we're going to multiply that by the probability of getting a dime. Okay, well, we took the penny out of the bag, so there are no longer 16 things in there. There are now 15 things in the bag. And how many of them are dimes? Well, 7 of them are dimes. So that would be the probability of getting a dime given that we already got a penny. And then we would just go ahead and multiply those two things together. And if you multiply them together and then simplify, this comes out as 21 over 80. Or 0.263. So that would be the probability of getting a penny and then a dime. Okay, so let's kind of do that same thing on this next one. So a basket contains 4 plums, 6 peaches, and 5 oranges. What is the probability of picking 2 oranges, then a peach, if 3 pieces of fruit are selected at random? Okay, so we want the probability of getting an orange, and then an orange, and then a peach. Okay, again, how many total fruit do we have? Four plus 6 is 10, plus 5 is 15. How many of them are oranges? 5. So the probability of getting an orange on the first draw is 5 out of 15. But we take out the orange, and how many things are we left with? Well, there's only 14 things left in our basket. And how many of them are oranges? Well, we already took one out, so 4 of them are oranges. So it'll be 4 out of 14. And then our last draw, there are now only 13 items in the basket. And how many of them are peaches? 6. So the probability of getting orange, orange, peach is those 3 fractions multiplied together. If you do that on a calculator, you'll get 200, no, not. If you do it on a calculator and simplify, you'll get 4/91, which is 0.04. Any questions about those type of problems? Okay. Let me see if there's one. Yeah, let's go down to your homework. I'm going to go to page number 5, and I'm going to look at number 3 with you. So it says, Tammy's mom is baking cookies for a bake sale. When Tammy comes home, there are 22 chocolate chip cookies, 18 sugar cookies, and 15 oatmeal cookies on the counter. Tammy sneaks into the kitchen, grabs a cookie at random, and eats it. 5 minutes later, she does the same thing with another cookie. What is the probability that neither of the cookies was a chocolate chip cookie? Okay, so we want the probability of not getting a chocolate chip cookie. Well, I'm going to use our complement notation and say we want not chocolate. Remember, a bar over the top of it means not. So the probability of getting not chocolate chip and not chocolate chip. Okay, well, how many total cookies are there? Go ahead and put in the chat how many total cookies we have. The total number of cookies. 55. 55. Okay. So 55 total cookies. And of that many cookies, how many of them are not chocolate chip? $33. So 33 out of 35 is the probability of getting not chocolate on the first draw. Okay. Now, what is the probability of getting not chocolate on the second one? What will the fraction be for getting not chocolate the second time? 32 out of 54. Correct. 32 out of 54 because we have one less cookie and one less not chocolate chip cookie. And then I'll leave it up to you to multiply those together and get your final answer. Okay. Questions about dependent events when you know the total number of items? Okay. Back to the notes. We got one more page to do. Not one more page, one more example. Sorry. So example number 9. Okay, so it says a cereal company conducts a blind taste test. 55% of those surveyed are women and 45% are men. 75% of the women surveyed liked the cereal and 85% of the men liked the cereal. Excuse me, what is the probability that a person selected at random is a woman who likes cereal, a man who likes cereal, a woman who doesn't like the cereal, or a man who doesn't like the cereal? Okay, so when we are just given percents like this, it's easiest to make a tree diagram. So notice on the last couple of examples, we had a total number of items. And so we could just think about how many items were left. Here we're given percents instead of total number of items. So we're going to make a tree diagram to help us find these probabilities. So we'll have our start. And then we need to show our possible outcomes. So we're interviewing men and women about their preference in cereal. So we're first going to know if they are a man or a woman. So man or woman. And it says 55% of those surveyed are women. So I'm going to put 0.55 on the woman branch to represent the probability of getting a woman. And then 45% are men, so that would be 0.45. These two numbers on these branches need to add up to 100%. Okay, then once we know that they're a man or a woman, then we know whether they liked the cereal or they didn't. So I'm going to say they like the cereal, and then again, I'm going to use complement notation. This time I'll use the little squiggly to say they don't like it. So this is like and don't like. Of the men, it says 85% of the men liked it. So this will be 0.85. And again, since these branches have to add up to 1, we know that the men who do not like the cereal is 15%. And then for the women, they can either like it or not like it. It said 75% of the women surveyed liked the cereal. So we'll have 0.75. And if those add up to 1, then we know that means 25% did not like the cereal. Okay, so now looking at part A, we're looking for the probability of selecting a woman who likes the cereal. Well, just like we did with our tree diagram earlier, all we'll do is we'll follow the branches. So we're getting a woman who likes the cereal, and we're going to multiply all the numbers that we pass. So we'll do 0.55 times 0.75. If we do that on a calculator, oh, my calculator just closed. We get 0.413. That would be the probability of selecting a woman who likes cereal. Okay, part B says a man who likes the cereal. So if we follow those branches, we get a man who likes the cereal. So we got 0.45 times 0.85. And we get 0.383. Okay, go ahead and do C and D on your own. And when you have finished, give me a thumbs up so I know I'm ready to move on. Again, when you're finished, just go ahead and give me a thumbs up so I know I can move on. Okay. Awesome. I think we're there. Okay, so a woman who doesn't like the cereal would be 0.55 times 0.25, which I got 0.138. Did you guys get that? Thanks. Okay, and then a man who doesn't like the cereal would be 0.45 times 0.15, which would be 0.068. Okay. Awesome, thanks. So you guys are getting those same things. Okay, let us go do one more from your homework, and then I'm gonna set you guys free. So this is on page 6. Okay, it says a department store employs high school students, all juniors and seniors. 60% of the employees are juniors, and 50% of the seniors are female, and 75% of the juniors are male. One student employee is chosen at random. What is the probability of choosing one of these things? So we gotta make a tree diagram. So we'll have our start. Since we don't have total numbers of people, we have to make a tree diagram. We're first going to know if we're dealing with juniors or seniors. We know 60% are juniors. So that means 40% are seniors. Then we know, then we're going to be either talking about male or female. Says 50% of the seniors are female, so 0.5, and if 0.5% of the females of the juniors are female, then the other 50% is male. And then it also says 75% of the juniors are male, so that means 25% are female. Okay, let's go ahead and just find one of these. A is, what's the probability of getting a female junior? Well, if we follow those branches, the probability of getting a junior is 0.6, and the probability of getting a female is 0.5. So if we multiply those together, we find the probability of getting a female who is a junior is 0.3. Did I get my juniors and my seniors mixed up? I did. 50% of the seniors are females, huh? Thanks, Emma. %75% of the males of the juniors are male. Okay. There we go. So a female who's a junior would then be 0.6 times 0.25. Oh goodness. Calculator keeps closing. So we get 0.15. Good, I'm glad you caught that. Helps me know that you really are paying attention. Okay, and then you guys can do the rest of those 3 on your own. Okay, so I'm just gonna quick go through the rest of your homework assignment and just help you understand, not help you understand, show you what your assignment is. So you should have already completed page 1 and 2 on Friday. So you need to complete page 1 and page 2 if you haven't already. On page number 3, we did number 1 together. I want you to do number 2 and number 3. You can skip number 4. Okay. On page 1, I want you to finish number 1 and do number 2, but you don't have to do C, E, or G. Just do B, D, and F. So draw the tree diagram and then find these 3 probabilities. On page 5, we did number 3 together, so just finish that one and then do number 1 and number 4. You can go ahead and skip number 2. And then on this last page, I want you to finish number 5 and do number 6. But you don't have to do B or D on number 6. Does anybody need me to repeat any of those homework problems? Okay, awesome. I am gonna hop off. You are too. Let me stop my share and turn my camera back on. But like I said in the announcement, I will be back on Zoom at 12:30, from 12:30 to 1:30, to answer any questions that you might have. So if you have the opportunity, work on the homework between now and then hop on Zoom if you're struggling with anything. Carson, no, you do not have to attend that one. That's just if you have a question that you would like some help with, then hop on. Okay, awesome. Thanks, everybody. We will see you tomorrow or later today.